Good morning. Thanks for joining us. This is Kevin Renaud. This is our 12th weekly version of our e-learning series, and today we're pleased to have KROHNE back. This time the subject is Coriolis Meters. We're just going to go ahead and get into it. So again, we like to start with the geography and the industries joining us. Today's interesting because we do have two countries joining us other than the US, one being India, and the other is a mystery country. So once again, we did this a few weeks back. If you know this country, go ahead and text it in the control panel, and the first 3 correct replies get a free Peerless hat. So while you're all Googling various countries around the world, I'm going to just briefly discuss the history of Peerless and what we're up to. Again, we've been around over 100 years. We've become known as a reliable source for process components that keep projects running smoothly and plants running efficiently. We have 3 divisions. Our Procore segment deals with OEM customers, our custom engineered equipment builders, and CapEx projects. Our process group works with our chemical, pharmaceutical, contractor, power, food, beverage, manufacturing groups. And again, our high temp division works with high temp insulation, refractory product, and laboratory and scientific surfaces. And the buildings to the right are where we were for many years and where we are currently. So once again, you may be familiar with Norm we met. He has been with us in the past doing this, District Manager Northeast, and Marty McLean is our US Sales Manager. From the Peerless side, we have Dan Morgan, we have Greg Barrell, and me once again. So again, many of you may remember that Norm, when he's not selling measuring instruments, he's playing musical instruments. And he does have an album to his fame. He wrote 12 of the 13 songs in it. And if you're interested, you can go here to find it. And judging on the price, it must be one heck of a CD. So it looks like there's only one left though, so you better rush there to get it. So Norm, nice work. So speaking of smooth voices, I am going to turn it over now to Dan Morgan, who is going to explain the control panel in our meeting platform and explain how you can play a role in it, today's meeting. Dan?
Yeah, thanks, Kevin, and thank you again to everyone. A lot of you are joining us again. I've been with us before, so you know the drill here. But for those of you it's the first time here, just want to explain how this is going to work. Basically, Norm's going to run through his presentation, and as he's going through it, if there's anything that you'd like a further explanation on, or have a question on, or maybe an application specific thought that you'd want to run by Norm, you'll notice there's a questions section in the control panel on your screen. So please feel free to submit anything, any thoughts, questions, comments that you have through that questions panel, and I will be keeping an eye on that throughout the presentation. And I will be finding moments to interject into Norm's presentation to hopefully get you any kind of answers or information that you need. So do not hesitate. And if you do know the answer to that country question that Kevin brought up earlier, we're still looking for some responses, and you can definitely throw those responses right in that same questions panel, and I'll be recording those. So yeah, that's that. Kevin, I don't know if it's there anything else, or we good to pass this on to Norm?
I am good to go.
All righty, Norm, I'm going to hand it off now.
Okay, good morning, everybody. And once again, thank you for joining us. We're going to be talking about Coriolis Mass Meters today. If you have any questions as we go along, feel free to throw them in there. So let's go ahead and get started here. Let's see now. Why is the arrow not advancing this? That's weird. Hang on. Wow.
Norm, you may need to click somewhere inside of the presentation first.
Yeah, I just did that.
Oh.
There we go. You're correct.
Right.
Okay, very good. Thank you.
Mm-hmm.
So when people think of Coriolis meters, they think of the traditional design, which was a bent tube design. Now, bent tubes, as you can see, come in a lot of different shapes, though. Okay, they can be single tube or dual tube, and like it shows there, U-shaped, V-shaped, triangular, Z-shaped. And this is what most people think of when they think of a Coriolis mass meter. And a lot of these different designs are still in use today, very much so. But a few years back, also we started seeing straight tube Coriolis meters, which have really changed the face of where people can apply these in a lot of cases and how they're installed. And we'll talk a little bit about that down the road. But again, in straight tube Coriolis meters, there are single tube, dual tube, and there's also quad tube Coriolis meters in the straight tube design and from various manufacturers. So, starting from the beginning, what is the Coriolis effect? Coriolis effect was discovered by Gaspard Gustave de Coriolis, a French mathematician specializing in mechanics, kinetic energy. He got interested in the transfer of energy in a rotating system. And so he defined the Coriolis effect as the apparent deflection of a moving object in a rotating system or rotating frame of reference. The principle is explained more practically if we take a look at a plane that's flying internationally. So let's say if a plane flies from South Africa to Poland, while the plane is in the air, the Earth is still rotating. So if the pilot didn't correct for the rotation of the Earth and tried to just fly in a straight line, and you were able to watch this from standing from the North Pole, the plane would appear to be moving in a curved path, when in reality it wasn't. But he would also miss his destination if he didn't correct for the rotation of the Earth. So therefore, the pilot has to correct during the flight to reach his destination successfully. Another way to take a look at this is look at a little playground carousel. So out in the playground, children's carousel. When the carousel is not rotating, and if you were to throw a ball from the center to the outer edge, the ball would roll in a straight line and would appear to those children on the carousel and those watching from around the carousel that the ball rolls in a straight line. But now if we repeat this with the carousel rotating, the children on the carousel see the ball curve in the path as it moves from the center to the edge. But those children that are watching from around the carousel will still see it going in a straight line. It will still appear as if it's going in a straight line. So if we take a look at the mechanical system of a Coriolis mass flow meter, and just for illustration purposes, we're showing this as a straight tube meter as opposed to a bent tube, but everything we say here will still apply. So there's a central driver that oscillates, okay? So it's oscillated by this central driver. The small oscillations are the principle used by the Coriolis mass flow meter. The fluid flows through the tube and tries, like the plane or the ball in the things that we just looked at before, it tries to travel in a straight line. So the fluid wants to travel in a straight line, but it has momentum. And even when contained in a tube, it continues to try to travel in a straight line. So because we're vibrating the tube and the fluid is trying to travel in a straight line, the inertia of the fluid distorts the tube with a force. And that's shown as F subscript C here. But the tube only allows the tube to deflect until the tube exerts an equal and opposite force on the fluid. And that would be F subscript R. So this is the reaction force, and this reaction force is implied by Newton's third law, which states that to each action, there is an equal and opposite reaction. So therefore, F subscript C is equal to negative F subscript R. The small deflection of the tube is accurately measured by the Coriolis mass flow meter. So we're measuring the deflection of the tube. So in a twin tube Coriolis meter, the driver vibrates both tubes, and sensors A and B measure the deflections between the two tubes. While operating, the driver oscillates the tubes with a vibration amplitude of only plus or minus 0.1 millimeters. So it's not a huge vibration that we see going on here. The vibration amplitude here in what I'm showing on the screen is actually exaggerated just to demonstrate the principle of what's going on here. The oscillation provides the angular velocity, which is stated by the W there in the little curved arrows, required by the Coriolis principle. The driver resonates the tube at the resonant frequency of the system. And we're going to be showing later that this resonant frequency can be used to measure the process fluid density in addition to the mass of the fluid that's going through. So we do get more than one measurement from a Coriolis mass meter, which we'll be taking a look at in a little bit here. So when there's no flow and the meter driver is not working, there's no vibration, therefore sensors A and B measure no deflections. When there's no flow, the flow velocity is equal to 0 and the mass of the unit of fluid in the tube has no inertia, therefore the mass exerts no forces on the tube walls. When there's no flow, the driver is running, the two sensors measure the same tube deflections at each end of the tube at the same time. So again, no flow. There could be liquid. I mean, there could be fluid filling the tube, but there's no actual movement, no flow. So what's going to happen is sensor A and sensor B will measure exactly the same amount of deflection. Therefore, there is no flow, and it detects that there's no flow and doesn't give us a measurement. However, when the flow is greater than 0, the inertia of the fluid mass tends to flatten the curve of the tube on the incoming side. So that would be at sensor A, in this case, because the flow is going from left to right, and push the tube outwards at the outgoing end. So it's going to cause that deflection that we're talking about. And with the flow greater than 0, the Coriolis meter continuously measures the deflection at both sensors A and B, calculates the time shift of the sinusoidal oscillation between the incoming and the outgoing sensor caused by the Coriolis effect. So if we take a look here, we look at the sine waves generated here. Basically, they are totally in sync with each other. Here we see that there is a separation there. So that time shift is what is going to measure the amount of mass that we have going through that meter. So we can draw the amplitude of the sensor measurement with time for both sensor A, which is shown in blue, and sensor B, which is shown in black. So that time shift is directly proportional to the mass flow rate. When the flow starts, there's a time shift between the measurements at sensors A and B due to sensor A seeing the tube accelerating, while sensor B sees the tube decelerating. This effect is caused by the deflection of the tube, which we talked about a little while ago. So the resulting time shift, as it states there, is directly proportional to the mass flow rate. So if the time shift increases, the mass flow rate increases, and vice versa. If it decreases, they both decrease. The Coriolis mass meter is actually a bidirectional device, very much like when we talked about mag meters a few weeks ago. We said that they also can measure in both directions. Coriolis mass meters, exactly the same thing. They can measure in either direction. So now we move on to the density measurement I talked about a little while ago. Coriolis mass flow meter can measure density independently of mass flow using a principle based on Hooke's law. So the Hooke's law spring equation states that for a spring with a spring constant and a mass attached to the spring, it will oscillate at a resonant frequency. The equation shows that if a mass is attached to a spring, it acts as a harmonic oscillator and will vibrate at its resonant frequency. From the equation, it can be shown that when the mass increases, the natural frequency decreases, and that the opposite is true. When the mass decreases, the natural frequency increases. So if we look at example A, where we have a 5 kilogram mass, okay, and then we're showing the frequency of oscillation, okay, when we plot the amplitude. If we were to increase the mass, we double it in this case to 10 kilograms. And again, remembering that the spring is the constant here in this equation. So if that is kept constant, then a larger mass will cause a lower frequency oscillation. Same is true for fluid that is going through a Coriolis mass meter. So if we relate the theory of Hooke's law to a Coriolis mass flow meter, the mass of the spring system, M, equals the mass of the tube which is fixed, plus the mass of the fluid in the tube, which is the variable within the process. So we have a fixed mass, we have a variable mass. The mass of the fluid in the tube is calculated from the volume of the tube, which is fixed, multiplied by the density of the fluid, which is variable. For a known meter, the mass and the volume of the tube are fixed and as a result are constant. Therefore, rearranging and substituting the equation, density equals the spring constant, divided by the frequency squared, multiplied by the fixed tube volume, and the constant 4 pi squared, less the fixed values of the tube mass divided by the tube volume. However, with all the variables fixed except for the frequency and the density, the frequency is inversely proportional to the square root of the density. The Coriolis mass flow meter continually drives the sensor at the resonant frequency, and by measuring this frequency, we calculate the density of the process fluid. So we're directly measuring mass, but because of all this other information that we have, we're able to calculate the density. And again, I know this, we don't need to memorize this formula. This is just to illustrate how the Coriolis mass flow meter is able to get or acquire the density measurement. That was the purpose of all of this. So having seen that the Coriolis mass flow meter can measure both mass and density, Coriolis mass flow meter can also be used to provide a calculation of volume flow rate and total volume. We have the information there. All we need to do is to do some math inside the electronics, and we're able to provide that measurement as well. So if someone wants to use a Coriolis mass flow meter, but they really actually want to get a volumetric flow rate, you can do that because the information's already there. And if that's what you wish to display in your DCS system or your PLC system, your HMI SCADA, it's very easy to do that because that information is already present within the electronics of that meter. So, and this is due to the fact that the volume flow rate equals the mass flow rate divided by the density. So if we already know the mass flow rate, we've already got the density. All we do is a simple division, and now we've got the volume flow rate. And we're able to provide that as information as an output or whatever, however it's required by the end user. So temperature. Coriolis mass flow meter has a third direct measurement capability, that of temperature. The process temperature affects the stiffness of the measuring tube with temperature. Also, temperature causes thermal expansion and contraction effects, which affect the stresses on the measuring tube. So to correct for these effects, the Coriolis mass flow meter measures the temperature of the measuring tube with a platinum resistance temperature detector, or RTD. The Coriolis meter uses thin wall tubes for the mass flow measurement enclosed in an outer case. So the RTD is and you're going to see in a second a photo that I have here. It's actually glued, if you will, for want of a better term, directly onto the measuring tube, okay? So you're really getting the temperature of the tube, but obviously the temperature of the tube is pretty much going to be the temperature of the fluid that's going through the tube. So the RTD, as I said, is actually bonded to the outside of the measuring tube with a thermally conductive gel to ensure good heat transfer to the sensor. This gives us a pretty good indication of the process fluid temperature, right? Therefore, the temperature data is also made available to the end user and the control system. So that is just another piece of information that it's not going to be as accurate as having an actual, temperature device that's right in the fluid measuring, but it's going to be pretty darn close. And it's there along with all these other measurements that are available. So having the density measurement, temperature measurement, that gives us another capability, right? So if we know temperature, we know density, we know mass flow rate, we know all this information, now we're able to also obtain a concentration measurement. Whether this is for API, Plato, bricks, Baume, or alcohol concentration, we're able to get that type of information out of a Coriolis meter as well. So again, We're able to get a concentration measurement because we've got all this other information available to us. And this just shows a photograph of where that RTD is actually bonded onto the measuring tube right there. So a lot of that was pretty complex, and I hope you were able to follow along. I hope I didn't go too fast, and I know there's quite a bit of information there in those first few slides, but let's try and simplify this a little bit, okay? So if we look at the measurement principle in simplified terms, right? Basically, we're going to vibrate one or more tubes that carry the fluid. Then we're going to precisely measure the frequency and phase of that vibration, okay? We have an electromagnetic coil that drives that vibration, powered by an amplifier circuit to vibrate the tubes at their mechanical resonant frequency. And now, because this frequency depends on the mass of each tube, and the mass of the tube depends on the density of the fluid filling the fixed volume of the tube, the resonant frequency becomes an inverse indication of fluid density. So now fluid begins to move through the tubes. The inertia of the moving fluid adds another dimension to the tube's motion. The tubes begin to undulate. And again, when I showed that one animation, that was vastly exaggerated. We said that typically you're vibrating at about 0.1 millimeter, right? So you're getting a undulation. You're getting this slight twisting action that's happening instead of just vibrating back and forth, right? Because remember, when there's no flow, the tubes are simply vibrating back and forth. As soon as we start to flow some fluid through there, now we get the Coriolis effect. Now we get the undulation, the twisting that's happening. And now our sensors, one at the inlet side, one at the outlet side, they are measuring that deflection. And by measuring that deflection, we're able to get the mass measurement. So the twisting, again, is directly proportional to the mass flow rate. And it's measured by comparing the phase shift between the motion at the entry point versus the exit point of the tube. The greater the undulation, the greater the phase shift, the greater the mass that is going through that meter. So another thing that we'd like to talk about is entrained gas management. So entrained air can happen in a lot of different processes. And typically entrained air is something that we don't want. In most applications, it is something that we try to avoid. We try to not have entrained air, or it can be an actual gas, entrained air. So places where we don't want it would be crude oil extraction, right? If we've got a pump that's leaking and causing some air to get into the system, we've got a pump that's cavitating, we've got some vaporization going on, we've got different liquids mixing together and they're not mixing in a homogeneous way, so we're getting some kind of air entrainment in there. Applications where, you know, we're filling and emptying a vessel or something like that, and obviously air. So one that comes to mind here is truck delivery in the dairy industry. When the trucks come in to deliver the milk to the processing plant, you're likely to get some air at the beginning when they first start pumping the milk out, and also at the end when they're almost empty. If we're top filling tanks and it's a long drop, that could also cause some air entrainment. So typically this is something we do not want. However, there are some applications where we do want air, okay? And so how do we work with that, right? How are we able to have that entrained air and still provide a reliable measurement? So in the manufacture of yogurt, mayonnaise, ice cream, okay, the final, especially in ice cream, the final product is frozen ice cream mix and air, right? This is what they call overrun in ice cream production. Your higher value or higher quality ice creams will have a smaller overrun, meaning they inject less air. Your less expensive ice creams will have a higher overrun where they inject more air. Being able to control this and being able to have an accurate measurement of the product with the air actually in there is very valuable to ice cream manufacturers. So again, We're looking at, there's the freezer, right? So ice cream production, right? The frozen and aerated ice cream is being pumped to the dispensing part of the process street, right? The challenge is to measure the accurate density of the frozen and aerated ice cream to verify the achieved quality in the final product, as well as the mass flow of the ice cream air mix. Okay, so what's the challenge? Well, it's precisely this aerated consistency that causes most meters to indicate a false reading. This was a problem for many, many years. Volumetric meters will over-report. So if this were a volumetric meter, like a magnetic induction meter, right? The ones we talked about a few weeks ago. A mag meter with a lot of air will over-report by at least the amount of entrained gas. Whereas some mass flow meters, Coriolis meters, will have trouble even maintaining a continuous measurement. This has been overcome in recent years by several different manufacturers with varying degrees of success. Some manufacturers are more successful at managing entrained gas. Some are less successful. But it's come a long way. So the fraction of gas that's entrained in the liquid can vary quite a bit, okay? A lot of things can affect this, right? So flow behavior is going to change. For instance, viscosity, low viscosity fluids such as water generally allow gas to move more freely. High viscosity fluids like honey, on the other hand, tend to retain gas. So often the viscosity and therefore the gas entrainment also changes with temperature. So a lot of things could be having a bad effect here on what's going on. Greater operating and vapor pressures and greater flow rates cause the gas to compress to some extent. So when we talk about entrained air, it's not just like this whole homogeneous mixture where we can predict, exactly how much air is in there, right? Because there's so many different patterns. So depending on the conditions of the pipe, different patterns of multi-phase flow might appear. These patterns we refer to as flow regimes. And there's a diagram here that indicates where the various flow regimes occur in horizontal flow, depending on the liquid and gas velocities, okay? So you notice we can have something like just tiny bubbles, or it could be a mist where the bubbles are even smaller. It could be a wave, and this would be bad, right? Because we've got air up on top and liquid on the bottom. It could be stratified even more. It could be just plugs of air. It could be just one giant slug of air that comes through periodically. These are all different ways in which air entrainment will present itself, okay, within the process. So again, density, viscosity, surface tension, all of these affect these flow regimes and how they will present themselves within our process. And here's a better look at all those flow regimes, okay, showing the gas and the liquid together within the pipe. So there's not always a direct boundary either, right? There's no sharp boundaries. So a change in physical parameters can change, can cause a sudden change in the flow regimes. There's, they don't necessarily have a sharp boundary where all of a sudden, okay, this drops off. You could be flowing from one to the other. So we could start out stratified, and then next thing you know, we're in wave or in slug, and we've got all this stuff going on, right? So because of this large variety in flow regimes, these all appear under what we call unsteady flow conditions. Multi-phase flow measurements can be very, very challenging for traditional Coriolis mass flow meters. So again, as I said, air and gas entrainment can cause many difficulties and make achieving an accurate measurement unobtainable in some cases for some manufacturers. Now, as I said, in recent years, manufacturers have come a long way in improving their electronics and everything else, and being able to better deal with air entrainment to varying degrees of success, as I stated before. So each manufacturer has their own way of handling air entrainment. Some do it better than others. So as an end user, you should always question the manufacturer's claims. Ask them for proof. So, you know, if they're telling you they can handle up to 60% entrained air and still give you an accurate measurement, make them prove it. Have them offer proof that they in fact can achieve this, or if they say they can handle whatever amount of air. Ask for specific examples and applications where they have successfully applied their technology to manage air entrainment. And if they're confident in their product and they have done this successfully in the past, they should have no problem with providing you with examples and application data showing where they've actually done this and were successful at doing it. So it's the old caveat emptor, right? Let the buyer beware, okay, is what we're saying here. So let's talk about calibration. We talked about calibration when I did the series on magnetic flow meters a few weeks ago. And calibration for Coriolis mass flow meters is a little bit different than with a, I mean, we're still going to run fluid through there, okay, to do our calibration. But there is a little bit of difference than with magnetic flow meters. So we need to establish calibration factors for the individual meter. All right, we need to know that it's going to meet the specifications as per our technical data sheet. And we want to have it calibrated so that the customer doesn't have to make additional corrections once the meter is installed. So the meters are characterized at 3 different temperatures, and water is used, and we'll explain why in just a minute. So typically 20 degrees C, 40 degrees C, and somewhere around 60 or 70 degrees C. Those are the 3 temperatures. So we run water through there, we take all kinds of measurements, and we're going to do it with 3 different temperatures of water. And what that's going to do is that's going to evaluate the behavior of temperature changes, how that meter is going to behave, you know, with these temperature changes. And we also want to be able to maintain the stated accuracy of that meter across that entire temperature range. So final verification uses established correction factors from characterization phase. Okay, flow performance gets verified. Then we produce the calibration certificate. Results for the cold water are used to verify accuracy produced on a certificate. Warm and hot water are used internally to verify characterization. So, right, we produce the certificate based on the 20 degrees C. The other 2 temperatures are for verification that what we did in that first run is actually accurate. And we can characterize that meter across that entire temperature range. This is just an example of a calibration certificate. This one happens to be in 3 different languages, English, French, and German. They look very similar, you know, from manufacturer to manufacturer. Standard calibration is made at 3 flow points, sorry, tongue twister there. 3 flow points and 2 or 3 repeats at each point, okay? So again, we're checking linearity. We're checking the combined effect of linearity and 0 stability, how stable it is at 0 flow. Okay, and actual flow rates obviously are going to depend on the actual size of the meter that we're actually calibrating at this point. In a custody transfer application, we typically do a 5-point calibration. Does not make the meter more accurate. Some people believe that a 5-point calibration will give us more accuracy. What it really does, it's simply an extra confirmation of the meter's performance that it will definitely perform within its specification under a custody transfer application. So it's just further proof that yes, this meter will give us this stated accuracy once we put it into our process. So again, we're establishing the meters within specification throughout the entire flow range of the meter, right? Allows the customer to range the meter without requiring new calibration. So here's the thing. Customer orders a meter, specifies a maximum flow of 100 tons per hour. His process changes, so now the maximum flow is 200 tons per hour. No new calibration required. providing the meter that was purchased could handle the entire range, obviously, but assuming it did, there would be no calibration required just because their maximum flow has gone up, okay? All they'd have to do is set their current output, their pulse output, or their display range, you know, within the converter, and that's just a very simple programming change. So mass flow meters are not dependent on fluid, okay? Some flow meters out there are dependent on fluid. Things like variable area flow meters are very dependent on what type of fluid that you're putting through them. But in the case of Coriolis mass flow meters, 1,000 kilograms of water, same effect as 1,000 kilograms of oil, okay? So therefore, there's no need to make an additional calibration because of a different process fluid, okay? All manufacturers use a very similar procedure for doing their calibrations, and these are procedures that are widely accepted by international certification bodies. Now, because of the wide rangeability, Coriolis flow meters can have a rangeability of 30 to 1 as high as 200 to 1. The same flow could theoretically be measured by 2 or 3 different size flow tubes. So we do a sizing and we come up with 3 different sizes that could handle our particular range. So using the smallest possible meter that will handle your range will lower the initial cost and will reduce coating buildup, but it's going to increase erosion and corrosion rates and head loss, which could lead to increasing pumping and operating costs. So it's a trade-off, right? You have to take a look at what is the best option here. Is the amount of money we're going to save on using the smaller meter going to be offset because of our pumping costs that are going to go up significantly over time? And if we were to look at that over a 1-year period or a 2-year period, or do we have abrasive material going through there and the higher velocity because of the smaller meter is going to cause too much erosion and we're not going to get the full life expectancy of that meter? So these are all things that need to be taken into consideration when sizing a meter properly. If we downsize using a meter that is small in the pipe, the process fluid, as long as the process fluid is clean and low viscosity, that shouldn't be a problem, okay? On corrosive, viscous, or abrasive, such as slurries, things of that nature, downsizing is not recommended, right? Because when you downsize, you have increased velocity, that's going to cause excessive wear, okay? Bent tube Coriolis meters will have a different pressure drop than a single straight tube or even a dual straight tube. Straight tube meters will always have a lower pressure drop than bent tube meters, okay? Again, these are things that have to be taken into consideration when sizing a meter and when looking at our application. A single tube straight tube Coriolis meter will have a pressure drop pretty similar to just a, say, a magnetic flow meter, because it's just a single tube, not a whole lot of restriction there, okay? And that's gonna generally give you your lowest pressure drop. So there are no Reynolds number limitations associated with Coriolis meters. And the Reynolds number, as I put down the bottom there, it's the ratio of inertial forces to viscous forces, right? It's a dimensionless number. It's used in the study of fluids as they flow. It determines whether a fluid flow is laminar or turbulent. If any of you were in the presentation we did on magnetic flow meters a few weeks ago, we talked about laminar flow versus turbulent flow. And magnetic flow meters are affected by that, which is why in a magnetic flow meter, we have straight run requirements. We have, on the inlet side of a magnetic flow meter, we recommend 5 diameters of straight pipe, and on the outlet side, typically 3 diameters of straight pipe. Coriolis mass flow meters are not affected by this. So therefore, they are insensitive to velocity profile, distortion, and swirl. So there's no requirement for straight runs of what's called relaxation piping upstream or downstream of the meter to condition the flow. Not necessary for a Coriolis meter. So installation, the meter should be installed so that it'll remain full of liquid so air cannot get trapped. So again, air entrainment is one thing, but if you've installed the meter in such a way that you've actually got a pocket of air that is consistently above that fluid, you're going to get less than satisfactory results here. So installation, Again, much like a magnetic flow meter, the best way is vertically with the flow going up. That's not always possible. A great many of these meters are installed horizontally, which is fine as long as precautions are taken so that we don't get that trapped air, as I just mentioned. In a sanitary installation in the food and beverage industry, the meter must also be able to drain completely. So the worst thing we can do is install it in a vertical pipe with the flow going down. That's also the worst thing you can do with a magnetic flow meter. So that is definitely not recommended. With newer Coriolis meters, now if you were looking at Coriolis meters, 20, 30 years ago, pipe vibration would have affected their performance. Most, not all, but most newer high quality Coriolis meters today are typically not affected by pipe vibration, as long as it's properly supported by the process piping. No special supports are needed for the flow tube, but standard piping supports should be located on either side of the meter. And that holds true for whether it's a bent tube or a straight tube. On either side of the meter, we should have some good support. But, these have come a long way in recent years. So again, typical normal pipe vibration should not really affect the performance all that much. So let's look at a few pros and cons. What are the pros and cons of a bent tube meter? Well, pros. Bent tube meters can give you very high accuracy, 0.1% to 0.05%. And you also get density, right? 100 to 1 turn down ratios, in some cases even higher. High and low temperatures. You can get bent tube meters that will work in cryogenic applications, very, very cold, up to above 750 degrees Fahrenheit. High pressures. You can get bent tube meters with 600-pound flanges, that can handle some really, higher pressure applications. They come in a wide range of sizes, anywhere from 1/4 inch to 12 inches. And we're talking about the actual tube size right now, or line size, I should say. You do have reduced mounting options with a bent tube meter. If you have a 12-inch diameter bent tube meter, the belly on that meter is going to be pretty big. So it is going to limit your options of how you're going to mount that meter. In some cases, they've had to actually dig a pit underneath the meter for that belly to set down inside that pit. And if you're trying to mount it vertically in what we call the flag position, a meter that size mounted vertically would require a whole lot of supporting infrastructure. So especially as you get into the large, smaller diameter ones, not so much. But as you get into the larger diameters, you do have reduced mounting options. They will have a larger pressure drop than a straight tube meter. So these are things to take into consideration. Now, if we go to the straight tube meters and look at the pros and cons of these guys, there are straight tube meters out there that still will give you high accuracy. Again, 0.1 to 0.05. We can still get a density measure. We still get good turn down ratios. However, we will get a lower pressure drop than we would with a bent tube meter. Easier to install because there's no belly. It's just a straight meter. Installation is much easier. If you can install the pipe there, you can probably install one of these there, right? Very easy to inspect and clean because you can basically take it apart and you can look right through the whole meter and see what's going on in there. Can't do that in a bent tube. You can't, unless you've got a small camera that you can drop down through there and do it in that manner. With a straight tube meter, you have secondary containment. The outer casing of the meter is going to be a much heavier material than the actual measuring tube or tubes, and will provide secondary containment in many cases. Now, that's not true of all manufacturers, but for many manufacturers, you do have this secondary containment, which for chemical companies and things of that nature, that's very important, because if they were to spring a leak inside the measuring tube, to have that leak contained could really provide a ease of mind for them right down the road. Wide range of sizes in straight tube meters, anywhere from 1/2 inch up to 16 inches. one of the cons is that they are more limited by temperature, right? 130 degrees C, which translates to 266 Fahrenheit, is about the limitation. And the reason for that is because it's a straight tube. So the tube is going to expand as the temperature goes up. And at some point, it has no room left to expand. It's going to be pushing against the end welds of the tube. And if we exceed the temperature too much, it's basically going to damage those welds, and then we'll have a failure. So we do have a temperature limitation. If you think of the bent tube meter, it can go to a much higher temperature because the tube's being bent, that V or Y shape or whatever it is can extend down, right? As the metal expands from the heat. So again, you can go to much higher temperatures with a bent tube design than you can with a straight tube design. So when we're selecting a Coriolis meter, if we're looking for low cost, yep, we can go with the lowest cost meter. We have to be willing to sacrifice a little bit of accuracy. And again, this is not a lot. So the lowest cost meter may give you an accuracy of 0.15 instead of 0.1. In many applications, 0.15 is probably good enough, or probably very very suitable for that particular application. So in this case, you can save some money by going with the lower cost meter. However, if you are requiring the highest accuracy possible, that will translate to a higher cost. So again, it's the cost benefit ratio here that you have to look at. If you require the lower pressure drop, more than likely that's going to lead you to a straight tube design. If it's a very high or very low temperature like cryogenic, now you're going to be going to a bent tube design. So those are the kind of the very small points to bear in mind when you're looking at an application and trying to decide which way to go. Having said all that, I am done. I thank you very much for being here today and sitting in on this presentation. And at this time, if anybody has any questions, we'd be happy to listen to them.
Thanks, Norm. Yep, awesome job. So far, we don't have any questions submitted right just yet, but we are going to be hanging around for a couple more minutes. So after digesting all of what Ron just went through, which is a lot of great information. Yeah, if you've got any questions, we'll be around. I'm going to switch this over to Kevin real quick. He's got a couple slides to wrap us up, but.
Thanks, Dan, and thanks again, Norm. That's certainly a lot of information. There's a lot that goes into these things, and we appreciate you being here once again. If we do have any follow-up questions, we'll be sure to get them your way. And again, we're here to help in any way. Anyone out there needs some help. Next week, we will be getting back with Hose Master for a corrugated metal hose. We've done choosing when to choose an expansion joint over a metal hose. We've done failure modes for expansion joints, and next week it will be specific to corrugated metal hose, proper application, failure modes, and certainly maximizing service life. So again, all our past recordings can be found on our website. We also will get involved in a tailored custom training if any company out there wants to get a team of folks together. We'll certainly tailor it to your needs. And again, we thank you for being here. We hope everyone certainly stays safe and healthy. And there will be a survey that you will see as soon as this is complete. And again, we do value your input. It's of great benefit to know which direction we need to go and what's working well and what maybe isn't working well. So once again, we appreciate it, and we will talk to you all next week. Bye now.
Thanks, everybody.